All right. Hello, guys. Welcome back to the integration section of our calculus course. Today, we're introducing 15.3, double integrals over polar coordinate. So basically, what this section is trying to teach you is a sort of U substitution method in high-dimensional integral. In particular, this is the case where we are applying the polar coordinate transformation in double integrals. So we will introduce general change of variables formula, the U sub, actually UV sub or UVW sub in, I think, section 15.7 or something, after we introduce the triple integral. However, we want to show you guys, first of all, a very useful change of variable in two-dimensional integration. So let us start. Today, we're going to evaluate the polar coordinate. So the idea is to transform a Riemann sum. So let us recall, a Riemann sum is basically you cut some region into very fine pieces, that is area. And for the height, you choose a specific point within that small area and evaluate that particular point, that the function at that particular point. So first of all, for now, we want to integrate over this area, which is the radius all the way from A to B, and let the angle goes from theta 0, which is alpha, all the way to beta. So basically, this sort of a bend thingy, difference between two sectors, basically. So the first task is to estimate the small area after chopping the large area. In this case, we denote it by Rij, where I corresponds to the radius region, Ri minus 1 to Ri, and J denote the angle region, theta j to theta j minus 1. So we see that the area for this Rij is actually given in this format. Recall that given a radius and given the angle, the corresponding area for the sector is given by half of r squared theta. So the large sector here has area half of Ri squared times theta j minus 1. Similarly, the small sector here has half of Ri squared times theta j minus 1. If we factor out the same part, which is theta j minus 1, then we have Ri squared minus Ri minus 1 squared. Using this formula, a squared minus b squared is a plus b, a minus b. You have Ri plus Ri minus 1, Ri minus Ri minus 1. So if we denote for convenience the half point of Ri plus Ri minus 1 to be Ri star, the midpoint basically, then we have that the area of this fine region is given by Ri star, the midpoint of Ri and Ri minus 1, together with delta Ri, the difference between the small partition of Ri minus 1 and delta theta j. So this yellow region can be given by this from the area. So now, if we replace the choice of point xi star and yj star by this particular choice of points, Ri star cosine theta j star, Ri star sine theta j star, where I denote sine j star by the midpoint. Oh, this should be j, so sine j star. So Riemann sum, the good thing about Riemann sum is that if you recall from our video in the section 15.1 is that the choice of point does not affect anything about Riemann integral. So in this particular case, I choose the midpoint, Ri star and theta j star. And the important thing is here. The delta Aij, the area for this fine region is given by this, right? So you have Ri star, delta Ri, and delta theta j. So if we take I and j, n and m, which is the partition number of this fine region, goes to infinity, then the mesh converges to 0, right? Every small partition converges to a 0 length partition. And then the left-hand side converges to the Riemann integral, double integral, over this region omega. And the right-hand side converges to f of r cosine, r sine, where you have an extra term here, r, right? RDRD data. This rectangle R will be referred to as Jacobian afterwards in the change of variable section. But for now, let us just remember that when you're changing variables in terms of R cosine and R sine, there will pop out an extra term R cubed. Okay. Obviously, in this case, the region is R goes from A to B and data goes from alpha to beta. So let us state the theorem clearly. If we're working with a particular, this should be called type 1 region, I think. So given a particular data, a constant bound, alpha, beta, and R has a functional bound depending on data. So different angles give different radius, say V1 data and V2 data. Then the integration over this integral, this domain omega, is given by f of R cosine, f of R sine, and there's an extra R cube. Don't forget this guy. And we integrate R from V1 data to V2 data. And data goes from alpha to beta. So yeah, this is the case where you are dealing with type 1 region. Obviously, you can also deal with a case where R has a constant bound and data has functional bound in terms of R. But this will be the most cases that we're dealing with because it is easier to understand. For different data, you have different integration radius. If for a radius, you have different integration data, that will be kind of a weird domain, and we don't really want to integrate that because in that case, it might not be a good way to apply the polar coordinate change of variable. So first of all, let us see the strength of this polar coordinate change of variable. Recall from our last slide, the section 15.2, we are integrating this function, x squared plus y squared, taking square root over this circle domain, right? This is a circle with center origin and the radius is 1. And if you guys recall, if you guys see the video, you know that we take a lot of time to compute that integration, right? We actually spend like maybe 3 or 4 pages to do a lot of U sub, in particular trig sub, and also IBP. So the complexity of that problem is because that we basically are using a rectangular coordinate, the Cartesian coordinate, to evaluate a integral, which is obviously of radial symmetry. So this function is obviously of radial symmetry, and this domain is obviously of radial symmetry. So the idea will be to apply a polar coordinate. Now, first of all, note that the set of omega can be written nicely in the R theta coordinate. So it is a circle with radius 1, and it goes from 0 to 2 pi, right? So theta goes all the way from 0 to 2 pi, whereas R goes from 0 to 1. So you can see that it actually is a constant boundary integration of omega. It is a rectangular integration for omega in terms of R and theta. So how do we apply this? First of all, you change your variable. So x and y are replaced by R cosine and R sine. And you change the boundary. So you have 0 to 1 with respect to R, 0 to 2 pi with respect to theta. Lastly, you plug this extra R cube. This is very important. Just remember there's an extra R whenever we're choosing the change of variable for polar coordinate. So this guy actually does not depend on theta because Pythagorean theorem tells us that cosine squared plus sine squared is always 1. So square root of R squared is R times R is R squared. So it becomes a really simple integration over a rectangle region, right? The integration of R with respect to R squared is given by R cubed divided by 3, and theta all the way from 0 to 2 pi gives you 2 pi. So the whole formula last will be 2 pi over 3. So you see that this is just a 2-line or 3-line proof, right? And previously we need like 3 to 4 pages to compute this using a lot of different techniques from single variable calculus. So the case where you want to apply this change of variable is whenever the integrand, the function itself, or the domain is of some certain radial symmetry, okay? In this particular case, both the integrand and the domain are of radial symmetric. So we are tempted to use the change of variable with respect to the polar coordinate. Okay, now let's do some more examples. So this example asks us to integrate this function 1 over x squared plus y squared over this domain. Xy belongs to R2. X is bounded within 1 and 2, so that is easy to understand, 1 and 2. And y has a strange upper bound, and 0 as a lower bound. So first of all, we want to understand what does this curve looks like, right? It is 0 up to some straight curve. And we can evaluate that. Y less or equal to square root of 2x minus x squared. After squaring both sides, you will get x squared minus 2x plus y squared less or equal to 0. Now we can complete the square by adding 1 to both sides, which on the left-hand side, you will get x minus 1 squared plus y squared that's or equal to 1. So the equality will hold whenever you're dealing with a circle with center 1, 0 and radius 1, right? Which is basically this red curve I drew here. I want to be in the interior of this circle, which is this part. Now, y have to be positive, so it is above. X has to be within 1 and 2, so it is this quarter circle, right? Okay, so basically we're dealing with a quarter circle of integration. And also the integrand is also of some sort of radial symmetric because we know that x squared plus y squared is always r squared. So actually there is no data involved here for now. That is why we want to apply the polar coordinate. So as I mentioned, let us first transform the integrand. It is 1 over r squared, right? So 1 over r to the 4, and you have extra Jacobian here, r. The difficult case here is about the boundaries. So actually the boundaries of r depends on theta, which you see that when theta is 0, r goes from 1 all the way to 2, right? However, when theta is, say, equal to 45 degrees pi over 4, you see that r no longer has any integration. It actually goes from what is this, root 2 to root 2. So there's nothing. So the region for r actually depends on theta. So we have to compute what is that upper and lower bound. So now let us draw an arbitrary theta within 0 and 45 degrees pi over 4. Okay, yeah, I forgot to mention this, but you have to solve this pi over 4 first, and it is quite simple because this is a 1, this is a 1. So an isosceles isosceles right triangle must have this angle be 45 degrees, right? So pi over 4. Now let us draw an angle theta within 0 and pi over 4. And let us solve like how long is this guy? When should we start integrating respect to r, and when should we end the integration? So for A here, it is actually quite simple. Let us take close look on this triangle here. You have 1 as a opposite of theta, right? So we know that OA in the denominator, which is the hypotenuse, and 1 as a opposite will give us cosine theta, which tells us that OA is actually second theta whenever this angle is theta. So next, we start from second theta, whatever theta is. For OB, there are so many ways to do this. One way is to use the, what's that called? The cosine law. This is a very naive way. We can see that later there is a more efficient way. But basically we have this angle, this length, right? This is 1. This is also 1 because we're dealing with a circle. So 1 squared plus 1 squared minus 2 times 1 times 1. So let us recall the cosine law. That is a squared equals to b squared plus c squared minus 2bc cosine c, right? Cosine a, right? In this case, the angle here is given by 180 minus theta and minus theta. So that's 180 minus 2 theta. And cosine of 180 minus 2 theta is simply cosine 2 theta. So you have 2 plus 2 cosine 2 theta. And don't forget the nice reduction formula for cosine 2 theta. It is actually given by 2 cosine squared theta minus 1. Plugging that back, you will have 2 cosine theta. And there's actually a faster version. So if you draw a perpendicular line here, and you see that this is 1, so by definition, this will be cosine theta. And this will also be cosine theta. So OB is simply 2 cosine theta, okay? So whatever you get, whatever you use, the actual answer where we start for the integration for r is from second theta all the way to 2 cosine theta. And theta goes from 0 to pi over 4. So you see that we have changed the integration region from this change x and y coordinates towards theta from 0 to 45 degree power over 4, and the region for r goes from secant theta to 2 cosine theta. And then it's actually really simple. So first of all, for this guy, you have 1 over r cubed, right? The integration for that is minus 1 over 2r squared, and you're plugging r to be 2 cosine and r to be secant. The first term gives you minus 1 over 8 cosine squared. The second term is plus 1 over 2 secant squared. And then this guy is basically 1 over 8 secant squared, which is very nice because we know the antiderivative is tangent. And this guy is again 1 over 2 cosine squared. So cosine squared can be reduced into cosine 2 theta plus 1 divided by 2. We have done this a million times. So at the end of the day, we get the antiderivative being in this format, and we plug in theta to be power over 4 and theta to be 0. Whereas we get the final answer to be power over 16. So I would say the whole concept ends here. This is the important part. We have to know how to translate the boundaries from these two guys into the boundaries in terms of r and theta. And we need to know how to replace the integrand in terms of r cosine and r sine. And we also need to add the actual r here, okay? So three things. One thing is the integrand, one thing is the Jacobian, one thing is the boundary. Those are three things whenever you're doing chain of variables. Whatever it is in 1D, 2D, or 3D. And I would strongly encourage you guys, whenever you see I did this, let's start the computation yourself afterwards, because this should be quite simple for you guys. That is the content for 15.1, right? Okay, so yeah, and I also encourage you guys to try to do this integration. You can see that it is very, very hard because the degree for y here is actually of power 4, right? And if you recall this, we can actually do this, but this will be very painful due to the fact that you are dealing with some sort of partial fraction, right? It is a polynomial divided by polynomial. And if you guys remember, that is very, very, very complicated. You have to do factorization, you have to do some tricks up, you have to do some logarithm. There's a lot of things going on. So whenever there is a radial symmetry in the integrand or the domain, then you apply polar coordinate. It'll make like simpler very, very much. Okay, for this third example, I want you guys to compute a particular area within two radial curves. So what do I mean? We want to find the area of the region within the curve r equals to 1 plus cosine theta. This is called a quadroid. And outside the circle, r equals to 3 cosine theta. So you can figure out what the curve looks like by replacing r and cos and theta by x and y. But I encourage you guys to try to do this, do the following sense. First of all, you draw r and theta in terms of like a Cartesian coordinate. So what theta corresponds to what r, and then you draw a curve, and then you analyze the curve to draw the actual curve on the xy domain. So for example, what is r equal to 3 cosine theta? It goes from 3 all the way to 0 when theta is power over 2, and minus 3 when theta is pi, right? And goes backwards. Similarly, r equals to 1 plus cosine theta starts from 2, right? Because cosine 0 is 1, and it becomes 0 when theta is pi, and 2 when theta is 2 pi. So how do you draw the red curve? Say the red curve. It goes from 3, right? So when theta is 0, it is 3. When theta is, say, power over 2, it is 0. So it goes all the way from here to here, okay? And for now, we can ignore the negative part because the radius will not be negative. You can understand it maybe in a sense like this, but for now, let us don't care about that. In general, we don't really care about the minus for the r because r is always positive. And for the blue curve, r equals to 1 plus cosine theta, it goes from 2, right? When angle is 0, it goes from 2. And when angle is power over 2, it is 1. So when it is power over 2, so pi over 2, which is somewhere here, this is pi over 2, the 90 degree, it is at a point 1. The radius is 1, okay? And then when you're dealing with the 180, it is pi. So 180 gives us the value 0. We have 0 here. So you see that 2, 1, 0. 2, 1, 0. Okay? And you do that again here. So this blue curve will be the chordroid of interest, and the red curve is the circle of interest. Now we want the region inside the chordroid, so inside the blue curve, but outside the red curve. So basically, these two very small thingy here. So the only task now is to figure out um, the angles of intersection, which you can solve very easily. We want to solve 3 cosine theta equals to 1 cosine theta, right? So that is cosine to be half, which is in this case theta to be pi over 3, 60 degree, or 5 pi over 6. So that's 2 points. And it can be shown here, here, and here, right? Okay, so now we can do the solving. So how do you integrate this? Area is basically the double integral over 1, right? On that particular region. We integrate, let me write it down. The area for omega is simply this guy, right? We integrate 1 over that region. So if you want to translate it into polar coordinate, you have to add the extra r here. Don't forget the Jacobian. And we change the boundary correspondingly. In this case, these two things are symmetrical, right? So then let us just put 2 here and evaluate one of the areas. So for example, in R, we see that for a given data, we go from the red curve to the blue curve, right? So it goes from 3 cosine all the way to 1 plus cosine theta. Basically, let me write it down here. In the xy domain, it is all the way from red curve to the blue curve. And it also reflects here. You go all the way from red curve to the blue curve. Okay. Right. So you have that 3 cosine to 1 plus cosine. And for theta, you have from pi over 3 to pi over 2. That is from the boundary point here all the way to the 90. Okay. Uh, Actually, technically, I'm not sure whether, let me see. Oh, sorry. I should actually change it. We didn't specify it as within the first and the fourth quadrant. So sorry. I should include this part. Yeah, see, there's a lot of silly mistake going on, something. Okay. So if I include this part, then the integration is no longer from pi over 3 to pi over 2. It should be pi over 3 to pi. Okay. So this will be the upper half, and the lower half have the same volume, so we don't really care about that. Okay. So basically all the way from the you know what? Let me change the answer for a bit because this will be a little bit complicated. We have to I understand the fact that this will be the red curve here will be 0 because there's nothing going on here. So let me write down this region, specifically region inside the chordroid, and in the first and fourth domain, just to avoid complexity. First quadrant. Okay. In that case, this will be this particular small ring thing. Okay, a green thing. Okay. You can obviously compute this by integrating 1 plus cosine over pi over 2 to 3 pi over 2, which is this part. Okay. But I don't want to do that here. I just want to follow the slide here. So you see that when we're evaluating this, then r gives you half of r squared, right? The half cancels out with this 2, and you have r squared minus r squared. And then it's simple algebra. So again, cosine squared gives you some sort of double angle, cosine 2 theta plus 1 divided by 2. And the antiderivative of this whole thing will simply be something like this. Plugging in the corresponding boundary point, pi over 2 and pi over 3, you get 2 minus pi over 2. So this small green region here, together with this guy, is 2 minus pi over 2, right? If you actually want to compute everything out, then there is this small small thing here, and you can compute that by doing this, evaluating the blue curve, pi over 2 all the way to pi. Okay, right. So we're done with this area problem, and I want to specify that actually you can we don't really have to draw a graph because the only thing important here is actually the boundary point. We know from this graph already that the region inside the quadrant and outside the circle is actually this point. We want to be below the blue curve and above the red curve. So it is this part and this part, in particular in the first and the fourth quadrant. So the only thing you have to solve is actually the boundary points, which is pi over 3 and pi over 2. So after solving those, you can simply write down integral. You don't really have to draw this graph. But this is obviously of important understanding. So try to do as many problems as you can in the area part of the section 15.3. It is very useful to use polar coordinate to evaluate areas for polar curves. Okay, so after the area problem, we have this volume problem. We want to find a solid within the cylinder, x squared plus y squared being 4, so it looks like this. It is a circle in the two-dimensional area, right? But z is not restricting now, so it is a cylinder. Okay, and we also have this 4x squared plus 4y squared plus z squared equals 64. This is a ellipsoid. It looks like this, a ellipsoid. Okay, so the volume is actually quite naive. Basically, you're integrating a volume, so you have this domain, right? In this case, the domain will be x plus y squared being less than equal to 4, a disk region. And the volume will be to integrate over this region of the height of each point. So in this case, the lower point will be the bottom of the ellipsoid. So you can solve z to be minus this whole thing. And the top will be the top portion of the upper bound will be the top portion of this ellipsoid. So you solve z to be plus this square root. And then it turns out if you're dealing with something that is very, very radially symmetric, so we are integrating over r from 0 to 2, right? The radius is 2, and we integrate over the whole circle. So it's 0 to 2 pi. And this guy will be 2 times root 64 minus 4x squared minus 4y squared, where if we turn that into polar coordinate, it's simply 64 minus 4r squared. And don't forget Jacobian, you have the r here. So you see that life is very simple now. You have an extra, what did I do here? Okay, yeah. So I factor out the 4 out of this square root, so you have extra 2. So you have 2 here, so you have 4 here. And this whole thing does not depend on data, so I integrate that out first. You have 2 pi. Finally, this guy can be computed using u sub, right? You can sub the u to be the interior, 16 minus r squared, and du is minus 2r dr, which is proportional to this r. And you get a really naive integration. Root u from 16 minus 0 squared to 16 minus 2 squared. And the final answer now will simply be 64 pi divided by 3 times 8 minus 3 root 3. That'll be the volume enclosed by the cylinder here, and also the ellipsoid. Okay, so you see that polar coordinate are really efficient in the integration whenever you have a nice integrand or a nice domain. In this case, the integrand is good. The domain is not really good, but since this will be very painful if you do the Cartesian coordinate integration, so we still change it into polar coordinate. And this is also efficient in finding the area for polar curves and finding volume for symmetrical objects, in this case, a cylinder or ellipsoid. Okay, now let us again introduce a very important integration. So previously, I think it's on the first lecture, 15.1, we introduced a integral that is called Te-Lun integral. So we apply the so-called Feynman trick to translate a single variable integral, which is sine x over x from 0 to infinity, and into a double integral, and then we start the calculation from there. So in this case, it is also a very, very classical trick on this Gaussian integral. And this is actually much, okay, maybe in some sense, much important than the Te-Lun integral. And I will introduce this guy more in 15.4. So we want to investigate this integration, e to the minus x squared from minus infinity to infinity. It is a one-dimensional integral. So first of all, technically we have to check that it actually converges. So we see that we can split this guy into, first of all, you can make it into from 0 to infinity times 2. That is because that this function is even. So the integral of this function from 0 to infinity is the same as from minus infinity to 0. So you have double that. And we split the 0 to infinity into two parts, 0 to 1 and 1 to infinity. The 0 to 1 is nothing because this guy is less than 1, so it's less than 1, right? The whole integration. And this guy, whenever x is larger than 1, is always less than e to the minus x, where we know how to integrate, right? This actually is something that we can do. So eventually, this guy is less than infinity, so this is a actual number. It converges. And so we can perform the trick that we're going to do. So the problem about this integration is, again, just like the duration of the integral, we don't really know the antiderivative of e to the minus x squared. And actually, we will not know. However, even if you don't know the antiderivative, you can apply the fundamental theorem of calculus. You can still find out this integral, which is kind of miraculous. You can see that this is the power of the double integration. We introduce an extra freedom. So if we denote this I by this Gaussian integral, then I squared is given by this squared times this, right? I use different notation of x and y to avoid confusion. So if we combine those two integrals, it is basically the integral over everything, right? We're dealing with minus infinity to infinity in the x coordinate and minus infinity to infinity in the y coordinate. So that's everything. And the integrand is e to the minus x squared times e to the minus y squared. So that's e to the minus x squared plus y squared. And you can see that the trick comes in. If we apply the polar coordinate, then we're integrating over every radius. So 0 to infinity and the whole circle. So 0 to pi. And you have e to the minus r squared here. And you have the extra Jacobian, which actually saves the day. Because you can do the u step, right? After u step, you can see that, so by u step, I mean, for example, you can do u to be r squared. Then you can see that this guy can actually be computed the antiderivative. It looks like this, minus half e to the minus r squared. So this extra r actually saves the day because we don't know the anti-differentiation of e to the minus r squared, but we actually know the antiderivative r times e to the minus r squared. By plugging r to be infinity, you get 0. R to be 0, you get half. So you have half times 2 pi, and that's pi. So the improper integral gives us I squared to be pi, and therefore I is simply square root of pi, okay? You will not guess that this guy actually has something to do with anything with pi, and turns out there is something in pi. So this is a very, very, very important integral in very many areas. One is improbability, and we're gonna introduce this more in the next section, the application of double integrals on subjects like physics, and also probabilities. So, yeah, I wrote a small remark here. So this is called a bell curve. Bell curve looks like this. There are some different scalings, but basically it looks like the Gaussian integral. And the graph of the bell curve looks like this. And the area under this bell curve actually represents some probability of certain events, which we will introduce more in the next section. But this is called a normal distribution, which is the most common distribution in some sense, that the middle portion has the highest probability and the tail portion have the lowest probability. For example, the distribution for the height within, say, UMN should be of normal distribution because you have someone which is really, you cannot have someone which is really high and really short with high probability, right? Most of you guys fall in a common region, which is somewhere here. Okay. Right. So let's go back to see what we have done today. We introduced a very nice technique in changing a variable. In this particular case, we're doing polar coordinates. So you will want to apply this technique whenever you're dealing with a region that is radially symmetric, or you're dealing with an integrand that is radially symmetric. For the first example, we see how we simplify the previous computation on this integration for 15.2, where we spend 3 or 4 pages to deal with this integration, whereas in this particular example, we spend only like half pages. And we deal with this example where the boundary for R is not constant with respect to data. So for different data, you have different boundaries and can solve that by simple geometry. And for this third example, we compute the area of between two polar curves using polar coordinate. In this fourth example, we compute the volume between some symmetrical surfaces, in this case, cylinder and ellipsoid. In the last example, we evaluate a one-dimensional integral using a two-dimensional integral and converting it into polar coordinate to show that the essentialness of this technique, because you cannot really do this using the ordinary fundamental theorem of calculus, since we don't know the anti-differentiation of so many functions. Okay, so that ends the double integral part. I will see you the double integral on polar coordinate part. I will see you guys in the next video, which we discuss the application of these double integrals. See you guys.